Hello! Today we're going to talk about an application of Dirac notation to spin in quantum mechanics. So mostly we're going to be thinking about spin as coming from electrons, but lots of other particles have spin as well. So the intrinsic angular momentum of a particle, so if you imagine a particle actually spinning, is called the spin of the particle. And so it doesn't just have to be orbiting around something, but it can be spinning a lot like a top or say a planet. And we're going to describe that spin by an operator S. And in fact, that spin has a direction, so we'll have a vector on it. And since it's an operator, we're going to have a hat on it as well. Of course, you can't actually think of an electron as spinning. It turns out it doesn't really make sense, but the electron still acts as if it's spinning, oddly enough. And so we're just going to assume that that makes sense for us. So when talking about spin, to start with, let's just focus on one direction of spin so we don't have a whole vector's worth. So let's focus on the z direction. So we're going to look at sz, the operator telling us about spin in the z direction. So spin is a quantum mechanical object, and so we're going to describe it by a ket, by Dirac notation. And so in particular, we're going to talk about in the z direction, if something is spin up, we're going to give it a ket with an up arrow, and spin down is a ket with a down arrow. And you notice I only gave you two choices, spin up and spin down, because oddly in quantum mechanics, there are only two choices for the value that you can get for the spin in the z direction. So it turns out that there are only two possible spins you could get for an electron if you were to measure the spin in the z direction. You get plus h bar over 2 or minus h bar over 2. Which again corresponds to the spin either being only spin up or spin down. You can't get something in between. You can't get a little bit of spin in the upwards direction. You can only get all spin up or all spin down, where all means this h bar over 2. It's kind of odd that spin is quantized in values of, or in units of h bar over 2. If you check the units of h bar, it actually has units of angular momentum. Kind of fun. But it's kind of odd that why did h bar show up here? It's just the fundamental quantum unit, and so it turns out that spin is intrinsically related to the value of h bar. So these spin up and spin down states are going to act like bra and ket states for us, and in particular we can construct a set of orthonormal states from them, or they are already orthonormal. Namely, if you were to take the inner product with up and up, you get 1. So it's normalized. Same thing with down and down. And up and down have 0 overlap. So if you take their inner product, you get 0. Okay, so that's introducing the idea of these spin up and spin down states. Let's talk about actually measuring the spin, how we would actually measure the spin. And the way we do this is with an experiment known as the Stern-Gerlach experiment. And to do this, let's start with a known spin. So let's say we start with a particle in a spin-up state. You send this particle through a magnet, and actually not just a magnet. The magnetic field has to vary with the z direction, but let's not worry about any of those details. So we send this electron with a spin up through a magnet. And since the electron with spin up, it's spinning, it's a ball of charge that acts like it's spinning, it has a magnetic moment. And so it turns out that the electron will feel a charge depending on whether it's spin up or spin down. So if it's spin up when it goes through this magnet, we'll get a force that goes upwards in the positive z direction. And if you have spin down, there will be a force in the negative direction, so it'll get pushed down. So generally, if you had any spin going through here, spin up particles would get pushed upwards, spin down particles would get pushed downwards. And then you can imagine putting a screen or detector in the up or down areas and see what you find, and try and collect the particles as they come through. And as a result, detect which particle you had that you sent through the magnet in the first place. Okay, but in this case, we sent a spin-up particle through our Stern-Gerlach experiment, through this magnet. And so we know that the probability to get spin up is going to be 1, and the probability to get spin down is going to be 0. And of course, we can answer that question by taking the inner product of the up bra with the psi ket. And when we take that inner product, we see that psi is all spin up, so we get 1 for that overlap. Absolute value squared still gives us 1. And conversely, when you take the inner product between down and psi, you get 0. So there is absolutely zero probability of getting spin down. Again, applying these ideas of Dirac notation and extracting information from Dirac notation to this completely different idea with spin. Let's now start instead with a randomized spin. By randomized, I just mean that I'm going to take a mixture of spin up and spin down here. So this is quintessentially quantum mechanics right here. We have a superposition of states, spin up and spin down. And you should think of this as a wave function being in a superposition of energy eigenstates in the same sense. So you could have psi1 plus psi2 plus psi3 in terms of energy eigenstates. You should think of this as the same sort of thing, that the wave function here is a mixture of both spin up and spin down. And so we don't really know what the spin is at this point. Namely, if you were to check, it is not an eigenstate of the spin in the z direction. So this particular state is not a definite state of spin. And that's what we mean in this case by randomized spin. It's not a definite state of spin. So let's send this particle through our detector. And we're just going to send one of them through. And we want to know, what are we going to get at the other side? Well, we know that there's going to be a probability to get a spin up particle. And the probability to get a spin up particle is going to be the overlap between the spin up state and psi. So do the bra and the ket of up and psi and take the absolute value squared. And then it looks like we get 1/2. So the probability to get a spin up state from this looks like it's going to be 1/2. The probability to get a spin down from this, well, also must be 1/2 then, because the total probability must be equal to 1. And indeed, if you take the overlap between spin down and psi and take absolute value squared, that will give you indeed 1/2 as well. Let's think a little bit about what happens if we were to chain together a couple different Stern-Gerlach experiments. So now let me start with that same spin state where the spin is not, or the wave function is not in a definite state of spin. I'll send it through the Stern-Gerlach experiment, except now I'm going to take the spin down particles, I'm going to throw them in the trash. I don't really care. So if it's spin down, I'm just going to make sure that those end up in the trash bin. But the spin up particles, I'm going to take any of the particles that were deflected up and divert them into another Stern-Gerlach experiment and see what I get at the end of that Stern-Gerlach experiment. Well, so since when the particles went through the first Stern-Gerlach experiment, the ones that didn't get thrown in the trash had to have been spin up, then that means that the input to the second Stern-Gerlach experiment were also spin up particles. And so as it goes through that second Stern-Gerlach experiment, our wave function now that we're keeping is only spin up. And so I have zero probability of getting any spin downs after that second Stern-Gerlach experiment because there were no spin downs to start with. So thankfully, that chain of reasoning makes sense with spin, that if you were to keep spin up and then keep making a measurement of spin up, you always get spin up. Again, this is that measurement hypothesis in quantum mechanics, which is once you make a measurement, the wave function now becomes that value, becomes that spin, and if you keep making measurements right afterwards, you're going to keep getting that value. So that's good. So again, the probability to get spin up in this case of chained Stern-Gerlach is 1, and the probability to get a spin down is 0. Okay, so in future videos, we're going to think about what happens when we have spin in multiple directions.